Hello and welcome to USMA Orgo. This video is about Chapter 1, which covers Lessons 1 and 2. The title of the chapter is The Basics, and that's what it's all about. Most of what is covered you've seen before, but it serves as a firm foundation for what we're going to be talking about the rest of this semester. So one of the things you'll start talking about is how to use the periodic table. And using the periodic table, well, you'll be able to figure things out, such as the number of valence electrons that something has. Like carbon has 4 valence electrons, nitrogen has 5 valence electrons, oxygen has 6, and so on. You'll also notice the electronegativity, which we'll talk about later in this presentation. So there's a lot of definitions in this chapter to refresh your mind about compounds, elements, atomic structure. So there's an example of the atomic structure there on the right. You also understand what valence electrons are, isotopes, covalent bonds, and ionic bonds. And when we talk about bonding, that's the most important part of how we use organic chemistry. So part of that is getting into electronegativity. Whether you get an ionic bond or a covalent bond is mostly due to electronegativity. So you should know the trends, that electronegativity increases from left to right and increases from bottom to top. So fluorine on the periodic table is the most electronegative element that there is. Then we'll talk about structures. You talked about Lewis structures in general chemistry, and some of the basic rules are on page 7 and 8. There's also some exceptions to the octet rule, which we'll talk about. And then they talk about calculating formal charge. They use this formula F equals Z minus 1/2 S minus U. I have an easier way of remembering that, and that's the formal charge equals the number of valence electrons minus the number of sticks minus the number of balls. What does that mean? You can calculate the number of valence electrons from the periodic table. The number of sticks is the number of bonds. Each line in a bond is 1 stick. And then the number of balls is each electron is considered a ball. So we'll talk about that more in class, but that's one way of thinking about formal charge, is the number of valence electrons minus the number of sticks minus the number of balls. Then we'll talk about isomers a little bit and get you familiar with the fact that you can actually take the same number of carbons, hydrogens, oxygens, and whatever other elements, arrange them in different ways and get different type of configurations, and that's what we're talking about with constitutional isomers. When we're talking about how to represent molecules and using structural formulas, so you can see we have the ball and stick model, electron dot formula, dash formula, condensed formula, and then the bond line formula. You'll probably see the bond line used often, but with all these structural formulas, you have to know if there's any implications on what they mean. For example, on the bond line formula, this carbon here, this peak, means a carbon with 2 hydrogens. And we'll talk about 3D structure. So a 3D structure allows us to write molecules in a way that represents how the atoms are arranged in 3 dimensions. So we would use lines and bonds along with these wedges and dashes in order to show that the wedge atom is coming out of the paper and the dashed one is going into the paper. Then we'll get into resonance theory. Resonance theory is explained on how to draw resonance structures on page 24, but that's basically knowing that you can move electrons around to different atoms and get different configurations, and that's what we consider resonance structures. And we'll talk about quantum mechanics and atomic structure. So first we'll talk about atomic orbitals, and we'll use things like the Aufbau principle, Pauli exclusion principle, and Hund's rule to give us atomic orbitals for different atoms. Then we'll take those atomic orbitals and we'll interact them with each other in order to try to make molecular orbitals. So if in the first case you have two orbitals that are interacting with each other and they constructively interact, you're going to get a bonding orbital. Whereas if you have two that are not constructively interacting or destructively interacting, then you're going to get a node, which is called an antibonding orbital. So over here we have a diagram that shows atomic orbitals of two different atoms combining to make molecular orbitals. So you take one and one, you get two molecular orbitals, one which is bonding, one is antibonding. So we'll talk about how to draw these molecular orbital diagrams for different, more complex molecules. Then we get into hybridization. Hybridization is combining orbitals in order to make other orbitals. So in this case, we're going to take one s orbital and three p orbitals. They're going to combine in such a way that we're going to make four hybrid orbitals, which we call sp3 orbitals. And then we're going to get into other type of orbitals, hybrid orbitals like sp2 and sp, and we'll talk about how they are filled and what they imply about geometry of a molecule and bonds, multiple bonds. So finally we'll talk about valence shell electron pair repulsion, which is how we can predict molecular geometry, which is on page 84. But for example, we have methane here where you can see that the bonds are 109.5 and they're as far away as they possibly can be from each other. We'll also talk about other types of configurations where, as you can see down here, we have ammonia, or even over here we have water. So one other thing I want to point out is that on page 47 there's a good review of some basics terms, and on page 54 is this chart, which has all the different concepts that we talk about in chapter 1, so you can go through and make sure you understand them. If you don't understand one of these concepts, you can go back to the section that it has to do with and review that section. So that's it for chapter 1. If you have any questions, please ask them in class. Don't forget to prepare for class, and I'll have a good day.